I'm gonna start recording and then share screen. Okay, and then we are here. So we start now. So una, dos, tres. So hello, I'm Mariana Vargas-Magaña from Instituto de Física, and I'm with Gong-Bo-Zhao from the National Astronomical Observatories of China, and we prepared together this video about the results from eBOSS for the late session. So this is part of the 3 videos that we prepare within eBOSS collaboration. The first one is about the introduction to eBOSS and cosmology. This is the second about the eBOSS, BAO and Multi-Tracer Analysis. And finally, in the early session, we will have another video with RSD analysis and void analysis. I'm gonna start directly with my part, that is the Baryonic Acoustic Oscillation within eBOSS. So for this, I'm gonna remind a little bit about what is eBOSS. eBOSS is the Extended Baryon Oscillation Spectroscopic Survey. This is a survey that took place between 2014 and 2019. The main scientific goal of this survey was to explore dark energy with using 2 observables, the Baryonic Acoustic Oscillation and the redshift space distortions. So we have 4 tracers for doing the clustering analysis, the Luminous Red Galaxies here on top, the Emission Line Galaxies here, the Quasars in 2 modalities, the first one as punctual tracers here, and we use also the Quasars as tracers of the intergalactic media through the fluctuation in the spectrum. So here are the numbers for the different samples as well as the redshift ranges. And if you want to hear more about the data itself, you need to go to the video 1 from Julian Bautista and Eva Müller. So the goal of eBOSS was to fill the gap in the redshift range of the measurements of BAO and RSD. Here is an example just for the distant measurements using BAO technique. And you can see that in the violet block, we didn't have any measurements before eBOSS, and the idea was to fill this gap. The same applies to the growth measurement that I'm not going to talk about in this video. So what are the Baryonic Acoustic Oscillations? It's a characteristic scale that was imprinted in the universe. This characteristic scale is related with a phenomena that happens in the early universe when the baryons were coupled with the photons. So they were in a kind of plasma where 2 interactions were happening. First, we have the gravitational attraction that makes that all the matter wants to collapse. But in the other side, we have the pressure of radiation that opposes to this compression. And this generates these density fluctuations that oscillate at some waves for all K modes. And we observe this in the configuration space. It results in an expanded spherical sound wave, as we can see in the picture here. So this expanding spherical sound wave propagates until the recombination time. At this moment, the recombination, the photons don't interact anymore with the baryons, and they can freely travel through the universe, and the baryons get frozen in these particular scales, as we can see in the bottom panel. So the final configuration gives place to this overdensity surrounded by a shell of overdensity of matter at a characteristic scale that is the scale of the BAO. So we are going to observe this around every single overdensity, as we can see from this video, and then we can observe these overdensities surrounded by these spherical shells at the BAO scale. So to extract the cosmological information, we make use of the clustering measurements using the 2-point statistics. In particular, we have here the definition for the 2-point correlation function. And if we compute this 2-point correlation function, separating along the line of sight and across the line of sight, we are going to get this kind of figure that we see here in the left side, where the BAO ring appears as here as a ring in this 2-dimensional correlation function. So we don't analyze directly this 2-dimensional correlation function, but instead we projected using the Legendre polynomials, and we analyze the multiples that we observe here in the bottom panel, the monopole in blue, the quadrupole in red, and the hexadecapole in gray. So we use this pattern as the BAO as a standard ruler. And what this means is that we know the size of this standard ruler, and we can measure the apparent size at different effective redshifts. And with that, we are tracing back the expansion history of the universe. So we can separate the BAO measurement along the line of sight and across the line of sight. And along the line of sight, it's gonna provide us information about the Hubble distance. And in the across the line of sight, we are going to have information about the angular diameter distance, as we can see here. So whenever it's not possible to implement this anisotropic BAO analysis, we can always extract information of the isotropic BAO analysis. And in this case, we are going to get information about the angular average distance, dB, that is a combination of the angular diameter distance and the Hubble distance. So now, in the current BAO analysis, reconstruction is part of the standard methodology. The reconstruction, the purpose of reconstruction is to enhance the BAO signal, as we can see here in this top figure. The idea of reconstruction is to undo the nonlinear bulk flux, and in such a way we can enhance the BAO signal, as we can see here, compared with the nonlinear that is what we measure from the spectroscopic surveys. And doing that, we reduce the error in the BAO measurements, as well as we reduce the BAO shift that we observe because of the nonlinearities. So here we have an example of the reduction of the errors that we can observe related with these processes of reconstruction. This is an example for the eBOSS data analysis with luminous red galaxies. We can see the comparison between pre-reconstruction and post-reconstruction for the angular diameter distance and the Hubble distance. So we apply reconstruction in eBOSS samples for luminous red galaxies and emission line galaxies. We couldn't implement reconstruction for quasars because it's a very sparse samples, and it was not possible to get a successfully inference of the displacement field with this sparse sample. So now I'm gonna pass very quickly to the BAO modeling. In general, the methodology for performing BAO fits is very standard. We use a template that is based in this anisotropic power spectrum. This template is composed of different ingredients. We have in green the modeling related with the nonlinear broadening, where we use two parameters for the smearing along the line of sight and across the line of sight. We also have a component that is for modeling the redshift space distortions. In red, we have the part coming from the linear redshift space, and in blue, we have the related with the small scales on the fingers of God. We have an extra component here in black that is related with the reconstruction step. And in this case, part of the reconstruction is a smoothing step. And this smoothing is covered by this smearing here in the SK. So in the case where we analyze samples that didn't get any reconstruction, we are gonna use an sigma R equal to 0. But in the other sample, we use 15 megaparsec average for all the samples. So we perform the analysis in both spaces, Fourier space and configuration space. And once we have this template that is fixed, given a fiducial cosmology that is imprinted here in the linear power spectrum, we are going to model the BAO peak using two dilation parameters. Dilation parameters along the line of sight and across the line of sight. These are the two free parameters of our fits that we are gonna use for fit the measurements. And together with this modeling of the BAO part, we are gonna include a model for the broadband shape that is using a polynomial fits in this part. The idea is that all the information about the peak is gonna be covered in this part of the fits, and the broadening is gonna just cover any mismatch, residual mismatch related with systematics or any residual mismatch of the model that is not related with the BAO peak. So with that, these alpha parallel and alpha perpendicular are directly related with the angular diameter distance and the Hubble distance. And this is for the anisotropic BAO. In the case of the isotropic BAO, we are gonna have just the information about the isotropic part coming from the monopole, and we are gonna extract information about the angular average distance, that is dB. So we test our methodology with mocks and that are listed here for any modeling systematics. And we have here 3 different kind of mocks that we use it for all eBOSS analysis. The easy mocks that were used basically for covariance purposes. We have a set of mocks generated by authoring for the different samples that are embodied mocks based. And then we have for LRGs that we also included analysis with N series that is an heritage from BOSS. So here in the right panel is an example of the behavior in the monopole for the different simulations compared with the data. Just an example of the kind of systematic that we tested in the papers. This is an example of the Luminous Red Galaxies, where we tested the dependence of the fiducial cosmology in the BAO fits. And we used the 2 simulations that I mentioned previously, EasyMox and N-series, in these 2 different colors. And you have here the fit of the mean with the error related in each case. And you can see that the systematics related with this fiducial choice is completely negligible. So I'm gonna go directly to present the rest of the results. So this is a plot that summarizes the BAO measurements from eBOSS. We have in colored panels what is related with eBOSS, and in the panels on previous SDS samples. We have in red the luminous red galaxies, in green the quasars, in blue the ELGs, and in violet the Lyman alpha forest. And this is the dV distance, the angular average distance. And these are the publications where you can find all the details of the clustering catalogs, the embodied mocks and mock catalogs used for the different samples, and the measurements, the BAO and the RSD, that in general are in the same paper. And just to conclude this part of the BAO, with this analysis, we provide the state of art of the BAO measurements for stage 3 spectroscopic surveys. We get this precision for the different BAO analyses in that are all of them between 1.8 and 4.1% measurements. In particular, the lower that we get are for the luminous red galaxies, that is 1.8. And the numbers for the Lyman alpha forest are coming from combining both analysis, the autocorrelation and the cross correlation with the quasars. And with that, we provide before the next generation of surveys, the most up-to-date measurements. So now we are going to pass, before passing to Gong-Bo's presentation, just a quick advertisement. If you want to hear more about the RSD measurements, you need to look the video for Hilmarin and Sechna Datu. That is your side, Gong-Bo.
Oh, great, thanks, Mariana. So Mariana just gave a very nice presentation on the BAO. Now I'm going to talk about the other stuff, which is the measurement of the redshift space distortions, because due to the peculiar motions of the galaxies. Next slide, please. Yeah, so this picture shows that the measurement of the galaxy clustering, starting from the Sloan phase 1 and 2 for the nearby galaxies, then to the current situation. Now we have surveyed about 2 million spectra up to redshift 2.5 or so. So from this figure, you can see that we have detected the BAO very nicely from different kinds of tracers. So then one naive question or natural question to ask is, why not we just cross-correlate different kinds of tracers that in principle could be very useful to beat the cosmic variance? Please, the next one, yeah. So eBOSS should be the first one to make it possible to probe the universe using multiple kinds of tracers within one survey. So next one, please. Right, so why cross-correlation is very useful? Because it can remove the cosmic variance. This is very easy to understand. For example, if we only have one tracer, so what you probe is the overdensity field, which is proportional to the matter field, delta, with some short noise. So whatever you do, you cannot avoid the cosmic variance because everything is proportional to delta. But if you have two tracers, for example, and what you measure is delta G1, delta G2, so they both are proportional to the same delta field, then you can basically take the ratio between these two. So what you measure then is this delta G2 over delta G1, which is independent of this Gaussian random field. So in the end, what you can measure from this is the beta, basically is the RSD parameter. So this idea was proposed by McDonald Seljack in 2002 and 2008 and 2009. Next one, please. Right, so the advantage of this cross-correlation or multi-tracers technique is that it can reduce the systematics because for the observation of different tracers, the photometry used for each one are usually different, so they are in principle uncorrelated. So it's much, much less subject to the observational systematics. Next one, please. And on the other hand, it can reduce the cosmic variance. So it can help with the statistical error as well. So this is the actual situation with eBOSS. You see these red dots are LRGs, the luminous red galaxies covering a large area. And the blue ones are for the blue galaxies, basically are emission line galaxies. They're young star-forming galaxies. So from this footprint, you can see there is a decent overlap between the LRGs and the ELGs. In area, it's roughly 800 square degree. And also there's a decent overlap in redshift between 0.6 and 1. So these are summarized in these two papers. The next one, please. Right, so this is the measurement of the power spectrum multiples for the LRG autocorrelation, ELG autocorrelation, and the cross correlation. One interesting thing you can see from this plot that in the ELG, for example, so this is the NGC, North Galaxy cap. You see there is some glitch on very large scales, which is probably due to the observational systematics. But if you look at the cross correlation, it looks much better. There is no such outliers on this, which basically says, proves that the cross correlation spectra is cleaner, basically. It is not, it's not contaminated by the, for example, the angular systematics. Yeah, please, next one. Right, so this is the corresponding measurement in the configuration space. You see everything is in the north again. So this is the left column is for the monopole, then middle one is the quadrupole, then the red one is the stackable. Again, this is the autocorrelation for the ELG and autocorrelation for the LRG and the cross correlation. Next one, please. Right, so this is actually the 2D correlation function and 2D power spectrum from the cross power alone. You see on the upper panels, those are the cross correlation 2D 2D power spectrum from this cross power. You see this one is basically tilted, elongated along the line of sight, along the K parallel. Basically that shows the RSD effect in the K space. And in the lower panels, you see the similar thing in configuration space. Again, here you see the 2D correlation functions for the ELG, LRG, and the cross correlation. So to quantify this, basically this is the full sigma detection of RSD from the cross power spectrum alone, which is pretty good. Next one, please. Right, so this is the measurement on the BAO and RSD from this autocorrelation and the cross correlation combined sample. In the end, we obtained two measurements at two different redshifts. Now the blue band is the Planck 2018 prediction. You see from the F sigma 8 plot, there is interesting discrepancy. Basically, it could be due to the residual systematics in the data, or it could be physical. This can be confirmed by the next generation, like DESI measurements. Next one, please. So this is the projected constraint on omega meta and omega lambda from our measurement. So by combining everything from BAO today, you see this gray, small gray contour. So that basically excludes the universe without omega lambda by 11 sigma. That is so far the detection with highest significance from BAO alone. Next one, please. Right, so this is the summary. So the eBOSS DR60 analysis is the most comprehensive analysis of the 3D map of the universe, filling in the gaps. And Sloan eBOSS with Sloan provide the state of art in BAO measurement for stage 3 redshift service. And we have successfully performed a multi-tracer study for the DR16 tracers and detected RSD from the cross correlation at 4 sigma level. And we gained a roughly 20% improvement on the RSD measurement due to the multi-tracer technique. And we found that the universe without dark energy is ruled out by 11 sigma level by the BAO alone. That's everything. Thank you very much.
Okay, so I stopped sharing.
Yeah.
Let me stop recording as well.